Good morning. In today's lecture, we are going to discuss about a basic steps involved in finite element methods. The finite element method may be described as a numerical method in which the unknown function of the problem domain is approximated by piecewise defined functions. That is, the complex region defining the domain or a continuum is divided into subdomains of simple geometric shapes, and the function is approximated separately in each subdomain by simple polynomial functions. The subdomains are called as elements, which are interconnected at some critical points, which are known as nodal points or nodes. The physical properties of elements like shape, dimensions, and the boundary conditions like external force, displacement, etc., are imposed on the subdomains, and the resulting elemental equations are formulated. The governing equations for the entire domain are derived as a summation of elemental equations leading to simultaneous algebraic equations which can be solved with the aid of computer. Here we are going to discuss about the steps involved in finite element methods. The first step, discretization of structure. The first step in the finite element method is to divide the given continuum or a solution region into subregions which are called as elements. Hence, the structure is to be modeled with the suitable elements. The number, type, size, and arrangement of all the elements are to be decided based on the accuracy required. Second step, selection of proper interpolation or displacement model. Since the displacement solution of structure or continuum under any specified load conditions cannot be predicted exactly or it is an unknown parameter, we assume suitable solution within an element to approximate the unknown solution. The assumed solution is known as displacement model must be simple from a computational standpoint, but it should satisfy certain convergence requirement. In general, polynomial form of solutions and displacement model is assumed. There are two types of displacement model, polynomial form and trigonometric form. The third step, derivation of elemental matrices and vectors. The elemental matrices, such as stiffness matrix for each element, is derived using various methods such as direct stiffness method, minimal potential method. Also, the elemental such as displacement vector and force vectors are derived and arranged in a suitable manner to obtain the equilibrium condition. And the equilibrium condition is given as k q is equal to f, where k stands for elemental stiffness matrix, where q stands for displacement vector, and where f stands for elemental load vector. Your next step, assembly of elemental equations to obtain a overall equilibrium equations. Since the structure is composed of several finite elements, the individual element stiffness matrices, displacement, and load vectors are to be assembled in a suitable manner, and the overall equilibrium equations has to be formulated as K Q is equal to F, where K stands for global stiffness matrix, and Q stands for global displacement vector, and F stands for global force vector. Next step, applying boundary conditions. A problem is incomplete unless a boundary conditions are specified. In fact, without imposition of boundary conditions, the element and global stiffness matrices become singular. Thus, boundary conditions are applied. Next step, solution for unknown nodal displacements. Unknown nodal displacements are found from the equilibrium equation of the continuum after applying boundary conditions of the problem. After the incorporation of the boundary conditions, the equilibrium equations are solved by various methods of handling of boundary condition, such as elimination method, penalty method, and multi-constraint method. Next, calculation of elemental strains and stresses. From the unknown nodal displacements, if required, the element strain and stresses can be computed by using the necessary equations. Next, computation of the reaction forces at the support. The reaction forces at the support are found using suitable formula-based method of handling boundary conditions. Thank you.